Hi and welcome to a new tutorial. Here in this video we are going to look at how to generate within the software the live load envelope shear and moment diagrams for a two-span continuous straight composite steel I-girder bridge. This is really following the Steel Bridge Design Handbook, one of the examples, which is available on the AISC/NSBA website. Here are the features of the bridge. We have multiple girders, cross frames mounted on stiffeners. We have a composite analysis where we're explicitly modeling the concrete deck. We are conducting an influence analysis as well as a moving load analysis. We have pin and roller supports, and we also have transitions and splices. We have four girders. Spacing is 10 feet. Deck elevation here, again, this is the distance to the midplane of the concrete deck. Here are the material properties for the steel and the concrete. We have 3 supports, with the center support being the pin support. We have 2 splices, 11 stiffeners located at spacing of 20 feet on both sides of the web. And we have 11 cross frames mounted on these stiffeners. I am applying a multiplier of 65% on the stiffness of the cross frames as per the latest recommendations provided in AASHTO to account for the connection eccentricity and the loss of stiffness that results from that eccentricity. I am modeling the deck in just one go because this is a pretty simple system, and I have a few additional reference points here. I don't need to click on this button as the model was already run, but if you ever change the reference points, whether braces, stiffeners, splices, supports, etc., you would need to click on it again. The mesh size is 3 feet. This is because we're running a live load analysis and influence analysis for which we are applying a unit load at each node on the deck. So we'd better have a coarse mesh, otherwise we'd run into time issues and it will take hours and hours to run. We have 2 profiles here with a thicker top flange in the negative moment region as well as a thicker web. We are assigning the different profiles here as shown in the NSBA design example. The same assignments apply to girders 2, 3, and 4. The elevation here is really following this profile, but here in reality the bottom flange has a constant thickness, so if we click on default we will see that the left and right elevations are always 0. And here comes the interesting part here. This is the form for the influence analysis. We are looking at 38 influence surfaces. The desired quantity here, 15, means that we are looking at the composite moment, and 16 here would be the shear. So this is grayed out as this quantity here, the composite moment, is really an integration of the stresses over the composite section. So it's not specific to a particular location on the cross section, which is why the software now just grayed out those cells. And the 5 here is just a convention. So we are looking at the influence surface at y equals 0, and then 10, 20, 30, 40, up to the end of the bridge, at least the end of girder 1. Well, then doing the same for girder 1, but now for the shear. The desired quantity, 16 here, is for the shear. Again, 16 here is the shear. And we're doing this at every 10 feet. So now you see why I had these additional reference points. This is because I want to be able to find the influence surfaces and the envelope shear and moment at every 10 foot along girder 1. This is the form where I define all the parameters for the moving load analysis. I have 18 truck models, okay? Here is the number of axles and distance between the wheels for each of the 18 models, and here I am entering the left wheel load and right wheel load for each of these models. And the difference here is that I am always adjusting the length between the second and the third axle. I am also defining a design lane load width of 10 feet. The design lane load magnitude is 0.64 kip per foot. I am saying that I will check 10 truck positions across the width of the design lane. I have 2 design lanes here. Each of them is 12 foot wide, and here is the location of the design lane with respect to the bridge deck. So here the center line of the design lane is at 7.5 feet away from the edge, which means that really 1.5 foot. So if we do 7.5 minus 12 over 2, that's 1.5 foot will not be loaded. We are also saying that we won't have any truck in the first foot on the left of the design lane, and we won't have a truck on the last 2 feet of the design lane. And then for the second design lane, of course, this is just 7.5 plus 12, the width of the design lanes here. So we will have 2 and 2 here for the minimum distances for the trucks. We are applying the multiple presence factors defined in AASHTO here. And finally, in this table, we are saying that yes, we want to conduct a live load analysis for all of these 38 influence surfaces. If you have any doubt about these parameters, there is this help button here, which goes over the individual parameters one by one. Now let's click next. The model is already run. It takes about 30 minutes to run, and this is no surprise because we are running an influence analysis for 38 influence surfaces, and then we have a total of 18 truck models, so no surprise. Here is the bridge. We can see the plate thicknesses here, and if we go to this view, a side view, we can see the assignments. Okay, we have this form to check the plate thicknesses. Let's go back to this view, and let's go to the influence surface radio button here. This is influence surface number 1, influence surface number 2, and let's scale this down. Okay, so the moment here, this is the influence surface for the moment on girder 1 at y equals 10 feet from the abutment for cross section node number 5. Here, this is we don't need this number because again, this is an integration of the stresses over the composite section. We can look at the truck configuration leading to this maximum moment, which is here equal to 9,600 kip inches. Can go to influence surface number 3. You can see that the maximum, of course, of this influence surface shifts, and we can go one by one, of course. If we were to check now the minimum value here, because we are getting close to the pier, it would be rather a minimum, it would be a negative moment. So here the truck would be located here. This is the critical truck position. Now let's go to influence surface number 10. This is really at the pier. You can see we would have 2 design lanes loaded, so a 12 point loads, 2 trucks, and then we go to influence surface number 11, 12, etc., etc., etc. So a really nice feature here to be able to find these influence surfaces on the shell model instead of applying the distribution factors, which is the 1D type analysis method. Let's just focus on the influence surfaces now. We are getting to the end of girder 1, and now let's go to influence surface number 19, which is the last one. Now it will be about shear. So V here is for shear. Let's look at the critical load configuration. We have 2 lanes, and again we have kind of this wave here which is propagating. Let's remove the loads here to make the sequence, to make the wave move faster and the model refresh faster. You can see this wave propagating along the girder. And again, for each of these positions, we can just click on this button to visualize the critical load position. So in particular, say here, if we go there, the maximum shear value would be 27 kips, and the minimum shear would be something different, would be minus 35 kips. And we can go till the end, so till the last influence surface, which is influence surface number 38. Now, something really useful that I want to show you is the ability to visualize immediately the envelope moment and shear. So here would be the envelope moments, the live load envelope moments for girder number 1. So you see positive moments at mid spans and negative moment at the pier, at the interior support. And same on the shear here, just really nice envelope shear diagram. So I hope this is useful. Again, we believe this is quite a nice feature to be able to visualize these envelope moment and shear for shell models instead of just using the distribution factors. Thank you very much.